Physics 203, College Physics 2, covers a wide range of topics. We start with electricity, from point charges and the forces they exert on each other through what are called electric fields. We continue with electric fields and their relation to what is called electric potential, the potential energy per charge stored in those electric fields. We also deal with devices that utilize this stored energy, capacitors. Electric circuits follows, the basis of much of our technology today. Magnetic fields are next covered. Like electric fields, magnetic fields are a means for exerting forces between magnetic poles. The exception is that where charges can be individually positive or negative, magnetic poles always come in pairs. This also leads to further components that can use magnetic stored energy in electrical circuits. Changing magnetic fields produces electric fields, and changing electric fields can produce magnetic fields, leading to the field of electromagnetism. Electromagnetic waves have a broad spectrum of energies and are broken up into specific broad names related to how they are used. We move to one form of electromagnetic waves called light, and explore all the ways that the wave nature of light leads to different phenomena such as reflection, refraction, interference, diffraction, and polarization. We conclude College Physics 2 by moving into what is known as modern physics. Relativity is introduced. Early quantum theory of the atom and the more general quantum mechanics follows. Finally, there is the study of the nucleus itself, nuclear physics, including the energy that can be released from those nuclei. Module 1 covers the majority of the course competencies of this text. The material covered can collectively be referred to as electricity and magnetism. These very broad topics cover much that we find in our everyday life, though in some cases it is so common as to not to be given much thought. Chapter 16 covers 3 of the course competencies of this course. 1. Explain the concept of charge and solve problems utilizing Coulomb's law. 2. Define electric fields and solve problems utilizing these concepts. And 3. Draw electric field lines about charges and dipoles and explain the concepts of electric field lines. When it comes to point charges, there is a similarity between them and the discussion of point masses covered in Physics 201, College Physics 1. You may recall Newton's universal law of gravity defining the force between pairs of masses and how, with care, this could be extended to more than just pairs. When it comes to point charges, Coulomb's law will come into play, appearing similar to Newton's universal law of gravity with one additional point. That is, with point charges, one can have both positive charge or negative charge, and the results can be quite different when bringing groups of charges together. Much as gravitational fields were a means of interaction between masses, electric fields will be discussed as a means for interaction between charges. Like the forces of interaction, electric fields are expressed as vectors. They have both magnitude and direction. Vector mathematics, covered in Physics 201, will be necessary to work problems involving both forces and fields, and electric field lines will be a means to picture the collective interactions between charges. Chapter 17 introduces the concept of electric potential. Electric potential is defined as the electric energy per charge of a group of charges. Since electric potential is related to the electric field, it can be used to find the magnitude, if not the direction, of the electric field for a charge or configuration of charges. Electric potential is a means of introducing energy and energy conservation to electric forces and fields. You might recall that energy was introduced in Physics 201 as an alternative means to solve problems, in some cases problems that might prove difficult to solve if one relied solely on force interactions. Electric potential offers the same possibility here, thus covering the course competency, define electric potential and solve problems involving these concepts, including equipotential surfaces. Chapter 18 introduces circuits and circuit elements. These are technological applications to the general forces, fields, and potential covered in the first 2 chapters. In our world today, electric circuits are all around us. Chapter 18 will specifically deal with the following 3 course competencies in simple circuit applications. 1. Define the concept of electrical resistivity. voltage, and current, and solve problems using Ohm's law. 2. Solve resistance problems involving series, parallel, and series-parallel combinations, including the use of Kirchhoff's rules. 3. Solve problems and define the concept of capacitance to determine the equivalence of series, parallel, and complex capacitive networks. Magnetic forces and fields are covered in Chapter 19, mirroring some of the application of charges introduced back in Chapter 16. The big difference in terms of fields and forces now is that magnets come in pairs of poles, a north pole and a south pole, rather than individual positive and negative charges. This changes a bit how we deal with forces and fields and magnets compared to electricity. This then covers the course competency, define the basic properties of magnetism and magnetic forces, include the use of the right-hand rule in solving problems. Chapter 20 addresses two more of the course competencies. 1. Define and use the concept of Faraday's and Lenz's laws. 2. Define and utilize the concepts of self and mutual inductance. Faraday's law looks at the effect of changing magnetic fields on electromagnetic force, first introduced back in Chapter 17. A bit of a misnomer, electromagnetic force is all about moving charges and is thus related to energy conservation. Energy provided by some means is transferred to energy moving those charges. Changing magnetic field strength, its direction, or both is found to have the same effect on charges as electric fields, thus providing another way of powering circuits. Lenz's law is more about determining the direction of the effect of the above-mentioned changes. It is less an equation-based relationship and more a direction-determination relationship. The type of change of magnetic field has a specific effect on the direction of motion of charged particles caused by that change. So Faraday's law can give us the strength of the electromotive force, or EMF. Lenz's law tells us the direction of the charge flow, or current. Induction is the process by which changing magnetic fields produce changing electric fields. This can have different types of uses in electrical devices, from transformers to storage devices called inductors. These store energy in electrical circuits for specific uses, which in turn expands the discussion of electrical circuits started back in Chapter 18. Chapter 21 concludes this module by dealing with the last course competency. Solve simple alternating current problems utilizing resistors, inductors, and capacitors. The circuits covered earlier use batteries to provide a constant electromotive force, or EMF, to drive currents through circuits. If alternating magnetic fields are used, a la Faraday's law, then the energy source can vary in EMF, causing the circuit to change direction over time. This is referred to as alternating current, or AC, and has broad applications in many of the electrical devices we use today. Each type has its own advantage and disadvantage, and this is explored in this chapter along with the different circuits that utilize AC. So Module 1 contains a hefty amount of material that may seem disconnected, but the topics are tied together when it comes to creating circuits. Whether direct current DC circuits or alternating current AC circuits, our technology today is based on the fundamental understanding of electric and magnetic fields and the force or energy delivery these have on charged particles.